Hi, this lesson we are going to talk about power. So power is basically how much energy you use in a certain amount of time. So power is equal to energy over time. Let's look at the units for power, energy, and time. So remember, energy is measured in joules and time is measured in seconds. And so power in this case is a new unit which is called watts, or essentially what it is joules over seconds. Pretty easy concept, I hope. You did learn this formula before in grade 9 electricity, but of course that was probably a really long time ago. All right, so there's other units for power and energy, and something that we use quite common is energy in watts hours. So if I rearrange this formula, so energy is now equal to power times time. That's a neat formula. We can also play around with units. So in other words, energy is equal to power times time. I can actually write it in a different way. Power measured in kilowatts and time in hours. And that's also a unit of energy as well. Okay, so yes, energy can be measured in kilowatt hours. Now, why do we need another unit like this? Well, we are energy hogs. So basically, you turn on a computer or you turn on a fridge or a light and you leave it on for hours and hours and hours. You're actually using quite a lot of energy, and that's why we use time in hours. And also, it takes a lot of energy, and that's why we use it in watts. And so your electricity bill is usually charging you in a rate of watt hours or kilowatt hours. So this is just another unit of energy. Another unit of energy. Okay, let's do an example. And what I mean by another unit of energy, it's another example you can think of is centimeters and inches. They both measure distance, but obviously one's metric and the other one is imperial. All right. So let's do an example where you can use kilowatt hours, and we use it all the time. If you look at your parents' electricity bill, it's measured in kilowatt hours or watt hours. All right, so here we have a toaster that has a power rating of 250 watts. So that's the power of the toaster. A family runs a toaster approximately 20 minutes per day, and if the rate of electricity is 12 cents a kilowatt hour, which is actually quite cheap, by the way, how much will it cost to run the toaster for 1 month? And we're going to assume 1 month is 30 days. So looking at our rate of electricity, it's measured in kilowatt hours. So we have to use energy or calculate how much energy you need in kilowatt hours to get how much it costs per day. All right, and so let's first do that. We have energy is equal to power times time. And the power rating of the toaster is 250 watts. Okay. That's in watts. And then we got 20 minutes a day. 20 minutes per day, but we also need it for 1 month. Okay, so let's actually kind of work this out a little bit better. But we need it for 1 month. Okay, so looking at my units, I need it in kilowatts. This is in watts, so let's convert. This is going to be 0.25 kilowatts. And the time I need it in hours, not minutes. So let's take our calculator here and figure out how many hours that is. So if I do 20 minutes divided by 60, that's going to give me the value in hours. All right, so that's 0.333. So I'm going to write that down. 0 divided by 60. All right, this is 20 minutes divided by 60 minutes to get you the hour. And we need to multiply this by 1 month, which is 30 days. All right, so 0.25 times, so 20 divided by 60, which we got this, times 30, and oh, there it is, 10. 10 hours. All right, so that's a total of 10 hours you are running that toaster. Okay, so there you go. Now we have our toaster usage, which is 2.5 kilowatt hours. That's how much energy you are using. All right, so let's actually calculate the rate. So if we calculate the rate, or the cost of electricity, the cost is how much energy you use times the rate. All right, so we're going to calculate the cost using the rate. So the energy you use is 2.5 kilowatt hours, and the rate is 12 cents per kilowatt hour. You'll notice that the kilowatts cancel out, and then you're going to get your cost. So your cost is now going to be, and we got our calculator, it's going to be 2.5 times 12 cents, and that's going to be 30 cents a month. Okay? So some of you are like, okay, that's not too bad. It costs 30 cents to run the toaster. All right? But that's just the toaster. And then you have all your computers, and then you need to charge your cell phone, and you got to, cook off the oven, in the oven or the stove or the fridge and the air conditioner and the furnace. So it does add up. So I do encourage you to, figure out how much is your electricity bill and why is it important to conserve energy. Now, about energy conservation, a lot of our electronics, our things that we use, aren't very efficient. And that's our next topic, which is efficiency. All right? So basically, how much of that energy is used to do the thing that you want, and how much of that other energy is wasted, or not necessarily wasted, but used to run the equipment. And that's called efficiency. Efficiency. And you can calculate it by two ways. You can either use energy or power, but don't mix and match. So you either convert everything to energy or everything to power. So I'm going to use it in the energy formula, or the energy definition first. So this is energy to do the job, all right? The job that you want done. And then this is the energy, and I'm going to write total energy needed to run the equipment to do the job. So there's a difference, okay? So for example, right now my job is to talk to you, but I also need to run my equipment like my digestive system, my heart, my breathing, flexing my muscles, pumping the blood. So I got to run my body plus the energy just to do the talking to you, okay? And so that's what we're talking about. In your formula sheet, I believe they call input and output energy, but most people don't know what that means. Here it is. Useful output energy and total input energy. But I prefer describing it so you have an idea of what that means. All right, because people are like, what do you mean by output? So this is output energy and input. I'll just write that down for reference, but really this would be percent efficiency times 100% if you want it in percentage form. But really, it's a description of the formula. Like I said before, you can also use power for this. So instead, you can actually have the power to do the job over the total power to do the energy. But remember, or to to do the job. But remember, you cannot mix and match, all right? So you either use power for both or energy for both. All right, let's do an example so you kind of understand what I mean by energy to do the job and then energy to run the equipment. So our first example here is boiling water. Okay, so we're going to boil water, but we're not going to make steam because I don't want to do a complicated latent heat example, although we can do one later if you like. So you're going to boil water, 2 cups to make your morning coffee. The kettle uses 500 watts. The temperature of the water is 15 degrees, and assume that the kettle uses 30% of its energy to heat itself up and the surrounding air. Now, notice 30% of the energy is used to heat itself up. So when you use the kettle, you're not only warming up the water, you're warming up the kettle. The kettle is warm to the touch, right? And then, of course, the air around it is also warm as well. So that's what I mean by total energy to run the equipment. What other things is the kettle warming up besides itself and the air and the energy to do the job, which is to boil your water? So 30% of that is used to actually heat other things other than water. So here's the question: how long will it take to boil the water? Now we're going to assume no steam is produced, all right? Now if steam was produced, then that means that's more energy that is used not boiling the water because it's converting it to something else, and it's not very efficient as well. All right, let's figure out how much energy it is to do the job. So energy to do the job. And if some of you want to write output energy, that's fine as well. Output energy. So you just want to heat the water to boiling. So when we heat the water to boiling, we have MC delta T. We are doing 2 cups, which is 2 kilograms. Sorry, not 2 kilograms, 0.5 kilograms, which is 500 milliliters, which is 2 cups. And then you have the heat capacity of water, which is 4,200. And then we are boiling it from 15 degrees to 100 degrees, but we're not producing steam. All right, we'll do that later. Work that all out, and it turns out to be 1785 and 2 zeros. So there you go. Now let's figure out the efficiency. Percent efficiency. Now remember, 30% of it is used to heat the kettle and the air. So therefore, only 70% is used to do the job out of 100%, for example. So then I write that out, and we're going to figure out how much energy you actually need to run the kettle. And this here is E total, or E input if you like. All right, or input. You can also write the total energy if you like. Cross multiply, and you end up with 255,000 joules. Now we need to figure out how long it takes. So now that you know how much energy it takes, which is actually this value, okay? You can't use this one, because if you use this one, then 30% of it is gone to heating the kettle. So we need more energy, so that some of it is used to heat the kettle and then some of it is used to heat the water. Okay, so just keep that in mind. This is water only. Water only. And this one is water plus kettle and air. Okay, and you have no choice. You have to heat up the kettle and the air. So let's do power is equal to energy over time. For example, the power of the kettle is 500. The energy you have is this 255,000 and over time. So let's figure out what time is. Time you figure out to be 510 seconds, which is approximately 8.5 minutes to heat the kettle up. And that's how you do efficiency. Bye now.